So coming to finding maxima and minima of a function in two variables, some of you have requested me to revise the topic as well. So I'm doing it. What do I do? Suppose if I have a function in more than two variables. See, it's obvious. Whenever I have to find maxima or minima, whether it's a function in single variable or two variables, it is one and the same, almost one and the same. What is it that we do? The necessary condition is that the first order derivative should go to zero. Okay. So similarly, since here the function is in more than one variable, I'll be having two first order derivatives, right? What are those? Dou f by dou x and dou f by dou y, right? Those two, I will equate them to zero. If I have three, I'll be having three first order. The function is in three variables, then I'll be having three first order derivatives. The first necessary condition is that the first order derivatives should go to zero. Next, what I will do, once I equate them to zero, I'll be getting two equations. Two equations, let them be 1 and 2. Solving 1 and 2 equations for x and y, I'll be getting a set of points called stationary points, guys. There's a word called stationary points. Okay. Now, what I will do, when does a function has a maxima for a function in single variable? When the second order derivative is less than zero at a point, then it will have a maxima at that point. If the second order derivative is greater than zero at that point, then the function will have a minima at that point. Same condition here also, but then we have a problem with functions in more than one variable, guys. What that is if I'm talking about second order derivatives, it's not just one like the function in single variable. Okay. Second order derivatives will be four in number. Okay. For a function in two variables, second order derivatives will be 2 power 2. Third order derivatives will be 2 power 3. Suppose if I have a function in three variables, then first order derivatives will be 3 power 1. Second order derivatives will be 3 power 2 in number. Third order derivatives will be 3 power 3 in number. Means 9 third order derivatives will be there for a function in three variables. Okay. 9? No, 27. Second order derivatives would be 9. So similarly here I'll be having 4. But then see here, what I'll give them some letters, because always writing f suffixes x's, typing or writing f suffixes x's or dou square f by dou x square consumes a lot of space and it takes a lot of time for typing as well, for which alphabets are being given R, S and T. How they are resulting, if you ask me, the derivative of f with respect to x would be called p, derivative of f with respect to y would be called q. So after p and q alphabets, I have R, S and T, right? Okay. Now fxy would be same as fyx. We have seen in majority of the functions, majority of the cases, fxy and fyx, both of them would be same. So taking them as 2, I just take 1 and then square it. Okay, that would be enough. Now t would be what? Second derivative of f with respect to y. Okay. Now I have a relation for the second order derivatives because they are 4 in number. I'll be having a relation which is a resultant of a theorem, okay, about which I'm not discussing here because we're talking only about the working rule of how to find maxima and minima, not the proof, right? So I have a relation like RT minus S squared. S, as I have said, is fxy and fyx as well. So instead of writing s into s, I'm writing it as s squared, or giving another alphabet for fyx, I'm just writing s squared. Okay. Now, for all the stationary points that I've got, ai, for I is equal to 1 to n. I assume that there are n stationary points. Okay, they can be 2, 3 in number. Now, what do I do for a function in single variable? As I have made a mention, second order derivative at that stationary point, if it is less than 0, then the function will have a maxima. Second order derivative, if it is greater than 0 at that point, then the function will have a minima. Okay. Now then, also I need to find this relation. This relation should always be greater than 0. The relation between the second order derivative should always be greater than 0 for the function in two variables to have an extremum, neither a maxima nor to either a maxima or a minima. To have, for the function to have a maxima or a minima, the relation between the second order derivative should always be greater than 0. If you ask me, ma'am, what if the relation is less than 0? If the relation RT minus S squared, if it is less than 0, then the function will neither have a maxima nor a minima at the point a1 comma b1. Okay, that means what? That point would be called a saddle point. Okay, what is a saddle? Where neither a maxima nor a minima is there. Okay, now what if this relation goes to 0? Now, the method in which I am working out is not giving me sufficient information So further investigation would be required to find maxima and minima. There are different methods like Lagrange method of multipliers, where I'll be using that method to find whether the function has an extremum value or not. Okay. Or in other words, RT minus S squared, if it turns out to be 0, I don't have sufficient information about the extremum value of the function. So I'll write the sentence further investigation is needed. Okay. Yeah, this is all about how I find maxima and minima. In the next lecture, I'll be discussing an example, okay, on maxima and minima.